recorded and will be available on the SDO 2021 website. So next up, we have Mr. Hugh Hudson from the University of Glasgow, and Hugh is going to be talking about EVE instrument and short-term solar variability. Take it away, Hugh.
Okay, thank you, Ryan, and it's thank you all of you for listening. It's maybe going to be a little bit repetitious because people have already talked quite a bit about flares and short-term variability and even EVE, but I'm restricting myself mostly to that very topic, the short-term variability that EVE gives us access to. And I'll just say, as a comment about EVE, EVE is a spectrometer. It has an order of 5,000 spectral bins, which are read out in the MEGS channels every 10 seconds. And so you can see that there's not very much data by comparison with SDO, with AIA, where there's so many pixels. And corresponding to that, there's a small community that works on the EVE data in flare physics. And so with that preparatory proportionality, let us proceed. So why is EVE and MEGS good? Limited angular resolution, only 1 pixel, namely the whole sun. Moderate spectral resolution, only 1 angstrom. That's really not great. But good spectral domain covering this whole range of 50 to 1,050 angstroms, and quite high throughput, in terms of photons per second, accumulated in 10-second time bands, which is already a very short time scale by comparison with scanning slit, long slit spectrometers, for example, which is such as ICE on Day. So if you go from like a 5-minute time cadence to a 10-second time cadence, there are windows of opportunity that open up for time domain astronomy in the sun. And I just, in this initial slide here, I'll just point to the future development of this. I think we ought to have more of this kind of thing. And we certainly want stellar observations with large aperture. EVE is a sun is a star kind of instrument. And so it's kind of a precursor to what we might learn about stars that are more complicated if we just have big enough aperture. And in the EUV, we would of course want to go to true imaging spectroscopy, both in the EUV and in soft X-ray bands with this kind of high time resolution. Okay, my slide does not advance. Oops, it does advance. So here's a very nice thermodynamic spectrogram that comes from the MEGS Spectra of EVE. This is 4 hours of a flare, and this is the temperature laid out on the y-axis. And you can see in the color scale here, this characteristic pattern of cooling at high temperatures. The flare fills the corona with hot loops and they cool off, and you can see that very nicely through the different spectral lines that EVE can give you access to. And also you can see this hot foot point phenomenon, the hot ribbon phenomenon that Paolo referred to in the low excitation lines. You can see all this very bright stuff early on. So this is a good graphic way to see these things. And this group from Hufei, I think it's maybe Rui Liu is the chief professor there. They've been doing quite a bit of work on EVE now, and it's quite good. So the other way to look at this overall distribution of temporal spectral behavior is just with looking at time series in a confusogram of this sort, which I call an iron cascade plot. It's only iron lines and ranging from iron 24 upper left down to iron 9 in lower right. And I'll show you a couple more examples of this. You can see several things here. And in this flare, you can, for instance, see the dimming here. This is very nice, a bit surprising to have seen that dimming. Okay, so what topics have been covered in the last decade using EVE solar data? Quite a few. And of course, the EVE group themselves, Tom Woods, Phil Chamberlain, Rachel Hawk, and James Mason have contributed quite a bit of it. But a lot of it has come, these are people who are mainly interested in EVE from its irradiance measurement point of view, whereas there are others of us who are doing solar astronomy as best we can. And so early on, it was clear that the data were good because you could see Doppler shifts. And even with 1 angstrom resolution, you can see down to 1 kilometer per second of Doppler motion if you're careful. as Ryan showed early on, 2012 paper, that the continuum are there, as was mentioned. Tom was very cheerful, very gleeful when he discovered that there was a new phenomenon that you could see with EVE, and that is what he called the EUV late phase. I won't talk about that. It was mentioned earlier in this SDO series. Ionosphere convection, I have a graph of that. Line ratio timing, I'm lighting up here in red some new things that I'll be talking about if there's time. Dimming, a big subject, and various very in a broad range of areas, including recently stellar dimming, a nice paper by Variability et al., just about to be published, or maybe it is published. The impulsive phase and high energy astrophysics are the two topics that I really want to talk about in my time here. And so let's get into the impulsive phase via the Lyman series. This is the only slide I have on this. I guess this is just a background slide showing you that one can see Lyman beta, Lyman gamma, Lyman delta, Lyman epsilon, and the Lyman limit. This whole range of blue pseudo continuum leading up to the Lyman edge in Stephen Brown's paper in 2018. And his main conclusion was that you really need better time resolution, but if you had it, and you might get it from solar orbiter, you can see these lines doing interesting things spectroscopically better than you can do it with 1 angstrom resolution. Okay, so here's another good example of the iron cascade plot. And I labeled this flare timing spectroscopy because one can see in the time domain, if one looks carefully, and you'll have to follow my cursor here, this peak here precedes the dashed line, which is the GOES peak. It's the iron 11. So this is Paolo's hot ribbon emission, and you can see it in all of the low excitation channels from iron 9 up through iron 13 very clearly, iron 14, iron 15. And not at all in the higher temperatures, but is that because it's not there? Not so clear. It may be that the breadth of the DEM is there, but it's being blasted away by the hot loops that are forming. So that item there lasts in this particular flare. This is August 4, 2011, and people have studied this flare from other points of view. Has this hot foot point property. So the hot foot points, as Paolo noted, were discovered by Yoko, and the famous flare of the 1990s was the Masuda flare, and you can see this hot foot point in the Masuda flare. It's very prominent. It's basically telling us that the evaporation process that we are familiar with in terms of launching chromospheric material into the corona to fill these hot loops really has to start with the chromosphere. And here's another excellent example, but just typical, from a paper by Kahn et al. In 2004. And you can see these two hot foot points. And so I think it is well accepted now that a lot of the physics that we think we may have thought was coronal in nature is now actually driven by foot point processes. And the chromosphere has always been a very complicated place, hard to decipher because of its small spatial scales and short time scales, but it's important. So let me just continue on that. So this is that flare again, August 4, 2011 flare blown up, and you can see that what looked like an impulsive pre-GOES brightening, called impulsive, actually lasted for 5 minutes in this event. So the impulsive phase, this is not atypical, can last for 5 minutes. It's impulsive because it contains within it very short time scales. And this is there are a couple of papers here. I've referenced Altintsev and Trevor Gnuth and Glazner on other aspects of these variations in this very flare, with the conclusion in the Altintsev paper that super Dreiser acceleration is what's happening here. And so the question is, how does the energy get into the chromosphere to produce these emissions that we see? And how is that related to the global physics of the flare itself? Particle beam, I don't know, but you can model it that way. So this is that flare again. Here's EVE carbon 3 transition region line. neon 7 showing you these impulsive variations, and iron 21 showing the slow variation. And if you blow up, this is the nice thing now, if you can blow up one of these peaks, and the one peak I've picked is the one between 0351 and 0352. So here's 1 minute of data, with 6 samples from 10-second cadence in each of these lines, oxygen 3, 4, 5, and 6. And you can see that EVE is telling us that oxygen 3, 4, and 5 are all pretty simultaneous, but that oxygen 6 may be lagging a little bit. And of course, one could actually, traditionally in recent days, one gets at this kind of time domain information by differentiating the GOES broadband X-ray signal. And when one does that, one gets a good proxy for the hard X-rays. And of course, to interpret what's happening here, we're thinking about ionization and heating. And this is showing you the time scale upon which it's happening. It turns out that almost nobody has used this capability in EVE, but there is the ESP branch of EVE, which has 1/4 second time resolution. So here I've rebinned this particular little burstlet into 1/2 second time bins, very high time resolution. And you can see that the peak here is identified to within 1 second. And there it is in coincidence with the MEGS spectral line observations, definitely preceding the oxygen 6 signal. Now, the question is, how do we interpret that? And the answer is, beats me, but it's something that if you ever could make use of a 1D radiation hydrodynamic model, you should be able to follow this kind of pattern and decide whether it's due to ionization processes, how deep it is in the chromosphere, and important physical things of that sort. And maybe analysis of more events like this would lead us to a better understanding of the energy transport in the impulsive phase. So this is just summarizes my thoughts about that. I just said these things, and so I'm reading them and they sound like I've already said them. So proceeding, the ionosphere, I just show this because it's so much fun. This is a Kakioka geomagnetic field showing what is called an SFE, used to be called a crotchet, a geomagnetic impulse. And you can see this black line, which is the magnetometer, terrestrial magnetometer, showing you the currents flowing in the ionosphere, responds very rapidly on a time scale of a minute to the impulsive phase, which is seen by Lyman alpha and in the GOES derivative, and also by EVE and helium-2, and the iron 9 line is a higher temperature line. It lags longer, it lasts a bit longer. But so this, and in the GOES derivative, you can see at the 2-second time resolution, you can see some of these QPP oscillations as well. So this is just a throwaway to point out that yes, the high time resolution is important for ionospheric effects, and I'm looking forward to hearing the talk on this very topic later on in this session here. Okay, and so this is the continua that Milligan found in EVE spectra, and I'll just emphasize this free continuum here, which is a very important, technically important observation that EVE is making, and in particular this 86 angstrom band right here, which I've isolated in a time series sense to compare with other thermal phase responses. And this is not high time resolution. This is, slow tens of minutes kinds of time scales. But you can see this continuum, the orange line here is very well matched in time with the Riston millimeter wave 15 gigahertz observation, which shows you the free continuum at very long wavelengths. These two light curves are spaced by 8 decades in frequency, and you can see this little sketch here shows how it works in the spectrum of the sun. In F nu, there's a peak where the photosphere is. It's sticking out at both ends. At the high end, there's the X-rays and this EVE 86 angstrom sample of the continuum, and at low frequencies in the microwaves, you can see the same flux, same spectrum. And the discrepancies that one sees in GOES are due to the metals, right? This is the astronomy term for having other elements than hydrogen and helium. And so there it's a little bit tricky to interpret because there is abundance variability and that sort of thing. But that's why technically it's very good that EVE gives us this clean 86 angstrom continuum point. Okay, now a couple of topics in high energy astrophysics, and then I'll end. One is the auroral Zerker effect, and one is a gamma ray event that I'll talk about. So the auroral Zerker effect, for people to understand this, and there's very little literature, but it's very interesting because this is how the hydrogen or the proton aurora was discovered on the Earth. It's charge exchange between high energy particles and in the auroral Zerker concept in hydrogen. In Lyman alpha, you should see wings. So as a function of displacement from line center, 10, 20, 30 angstroms, one should see, depending on the parameters of the precipitation model of protons or the SCPs that are interacting with the solar atmosphere, one should see bright wings. And by analogy with that, I looked at EVE 304 to see if alpha particles, which would be helium, could actually be detected. It's never been observed in hydrogen, but there's never been good observations in hydrogen, as a matter of fact. But EVE gives us good observations now in helium, and the answer, unfortunately, is the same. It's not there. So one can only conclude that there are quite a few very plausible assumptions that are made in the theory, and they're just not allowing us to see these particles interacting with the dense atmosphere. And why is that interesting? Because now one of the more important solar physics problems, I think, is identifying how the Fermi gamma ray observatory long duration gamma ray events work. These are, if you're not familiar with it, these are events which last for hours following a flare, and there's no known optical counterpart. So I think there's an avenue of opportunity here for us to study, for instance, with the SDO data to see if we can find some signatures that would let us identify where these things are. And this is a case of a limb occulted Fermi gamma ray event that EVE detected in 304 in this very impulsive way, a very brief time frame following the type 3 bursts, following just the very initiation of this thing we can't see. It's behind the limb. This is all in the corona. And you're seeing it in EVE 304, but also you're seeing it significantly in iron 21 and other high temperature lines. And so, and here you can see the dimming as well. The dimming is in the high altitude corona. This event, the flare itself is 20 degrees behind the limb. And so all that EVE sees is the global corona. And you can see the dimming happening as a result of the flare disturbance and the CME ejection. The interesting question, which I haven't resolved, just got excited and worked on this during the last week getting ready for this talk, and this is either the filament going out or it's the front of the CME that is producing these high temperatures. And so I'm looking forward to doing more work on this after I finish this talk, and I am finished. So I just wanted to conclude by saying that this is, EVE has expanded our parameter space for time domain spectroscopy. And this illustration that I got from a seminar presentation by Cecilia Aguilar just last week just shows you that on a stellar time scale, one sees stellar radii and parsecs, and one sees months and years and centuries, all coupled by velocities of things that stars respond to. But in the case of the sun, of course, we have higher time resolution. So this whole domain, time domain astronomy, it can be done sort of down to the milliseconds, if you wish, for instance, as people do with solar radio astronomy. So there are plenty of good research areas in the EVE data, and I think I pointed to one or two of them here in terms of the time domain ionization balance or non-equilibrium development that really requires hand-in-hand work with modelers to try to identify the physics for, but that EVE will give us some quantitative information for. So thank you very much. I'm quite finished.
Thank you very much indeed, Hugh. It was a wonderful review of an instrument that I'm very familiar with myself, and good to see it being put to more use than it was originally designed to do. Georgios, any questions or comments in the chat there?
We have a comment from Jean-Claude Vial. He says that with UVSP and solar maximum emission, those old missions. Basically, the OV oxygen 5 emission coincided with hard X-ray impulse. The oxygen 6, which is lithium-like, has an extended wing towards high temperatures.
Right, and it's interesting. Thank you, Jean-Claude. This could be ionizing, right? It could be that the chromospheric plasma is heating up and that the higher ionization states are coming later. But my own preference physically is for a discharge phenomenon in which everything happens simultaneously. And so I'm a little bit chagrined to see that sequence in that particular little micro burst that I showed you. But since it's the only one that people have looked at, there's still plenty of room for me to be right about this. and I do appreciate UBSP. That was a wonderful instrument, almost forgotten by people, I'm afraid.
Okay, thank you once again, Hugh. I think we might have to